Hello everyone, welcome to part 2 How Go Scheduler Works. My name is Rajan Joshi and I have 10 years of experience as a software developer. From last 5 years I am working in Golang and various other tech stacks. Primarily my majority of my projects lies into cybersecurity domain. I've been working containerized and non-containerized environments, developing REST APIs, gRPC, daemon applications, socket-based application and much more. Let's take a recap from our previous video. So in our last video, we understood two concepts: cooperative multitasking and preemptive multitasking. Both of these are required to understand how Go Scheduler works. In cooperative multitasking, an application decides whenever it wants to give away the processor time. And in the preemptive multitasking, instead of an application deciding it, operating system decides whether processing time should be given to a particular application and for how long. And this was done through thread scheduler. Thread scheduler. Let's see, these are the topics that we are going to cover in today's video, which is execution path, parallel execution, and thread pools. We'll try to understand each of these concepts, and we'll try to link at a very high level how my previous video and this video is related to Go Scheduler. By default, applications have one execution path, which we usually call main function or a default function in many languages. It has a start point and an end point. From first point to last, executions are executed in some manner, usually sequential. Let's take this example. There's a function main, and there are two function calls being made: function 1 f1 and function called f2. In this manner, f2 will execute only when f1 execution is completed. Now, this is justified if f2 or the execution of f2 depends on output of function f1. But what if execution of function f2 is independent of f1? If there is no dependency of f1 on f2, why should f2 wait for f1 to complete its execution? Now here we need to understand what is execution path. Take this example. Here we understand. Here in this part, application 1, we see this is a main application. These are the instructions, and let's suppose these first 10 instructions are for function 1 and the rest of the instructions are for f2. The same thing, function f2 is going to execute after f1, but since the execution of f2 or f2 is entirely independent of f1, so we can say that if there is any way to execute these two things independently, then it should be good. To execute f2 independent of f1, f2 needs its own execution path, and the way we achieve this is through creating one more execution path. I want one more execution path for f2. Currently, it is the same execution path of main, which is the execution path 1. But I want f1 and f2 execution independently, since both of these functions are independent in nature. I can create one more execution path to execute f2 independent of f1. How do I do that? Let's understand. First of all, try to understand how operating system plays a sequence of instructions. This is done using a thread. So application 1 will borrow one more thread, T2, from OS for same application app1 and schedule execution of function f2 through the particular thread here. But we still have only one processor or one CPU here. So we even though if we create two threads, T1 and T2, entirely for function 1 and function 2, Will they be executed at the same time? No. They can be put into execution at the same time, but they won't be getting executed since the processing unit is one. The processor can still execute one instruction at any point of time. But what if processor can execute only one thread at a time? Why do we need multiple execution paths or threads within same application? Application 1 will get more processing time by creating one more thread. How we design multiple execution paths for our application? Through operating system thread. Till now we have discussed application with one processor with one core. Before moving ahead, I would like to give you a recap here. There are two functions, function 1 and function 2, which were being executed in a sequential manner. There was one execution path, so it means executions will be done sequentially. First, if F1 will execute, F1 execution is done, then F2 execution will begin. Since nature of these two functions are independent, so we have tried making a different execution path so that these two can execute at the same time or can be put into execution at the same time. This is done through a new thread in operating system. Function 1 or F1 will be handled by thread 1 and F2 execution of F2 will be executed by thread 2. Here the bottleneck comes here is since we have only one processor, so no matter we have 2 threads or 3 threads, there is only one process that will go into execution at a time. Let's now do multiple processors approach. In this scenario, there is a possibility thread 1 might be created for processor 1, thread 2 for processor 2. Now when this happens, what do we call this? We call this parallel execution. Since we have two processors available here, so it means they can execute one thread at a time individually, and this is what we call parallel execution. One more thing very important here. This is why we say concurrency is not parallelism. Concurrency is the design underline under which application and application 2 parallelism is the execution. I'll rephrase it. Concurrency is not parallelism. Concurrency is the design, parallelism is the execution. Next point here should be concurrency is not parallelism, but concurrency is needed to achieve parallelism. How can we say that? First of all, we need to let's consider application 1 here. They have two different execution paths for F1 and F2. Two threads are created, one for F1 and one for F2. There are two processors, so one processor can execute thread 1 at this thread 1 and second processor can execute thread 2 at the same time. So this is why we can say this design of our application is called concurrency design, and the execution, the way processor handles it with multiple processor is called parallelism. That is why concurrency is not parallelism, but it is required to achieve parallelism. They can be concurrent executions without parallelism. How I can say this? In this manner, function F1 and function F2, even though if there is one processor, the two threads can be created and they can be executed alternatively. So this is concurrent execution but not parallel execution. They can be possible to have multiple execution paths but without possibility of executing them parallelly or at the same time. That's why we say concurrency is required for parallelism, but it's not parallelism. Backbone of this model is operating system threads, but this is also one of the main concerns or challenges for this approach, as operating systems are notoriously costly. How are they costly? In Linux, a thread requires almost 2 MB of memory. So let's suppose if you are trying to execute 50 threads, so 50 into 2, 100 MB of memory space will be required just for execution of your thread. Apart from this, there are a few other memory space which is required by required by any application to store the application, and for various other reasons, so that will additionally added on the top. Let's understand what is a context switch. Switching from one thread to other thread is called context switch. In other words, whenever a processor switches execution of one thread to the other thread, that is called context switch. What is the process? So what happens is, we assume there is one thread which is getting executed and thread 2 which is waiting to get executed. Now processor what processor will do is, first of all, when the allocated time for that for thread 1 gets completed, processor saves the current state of thread 1 somewhere, check if there is any available location, or if there is any available data for thread 2 to resume. It will pull up, or otherwise it will put thread 2 into execution. Now after some time processor time for thread 2 will also get elapsed. So the processor will follow the same step. It will save the state of thread 2 and restart the execution of thread 1 where it left the last time. This unloading and loading of states keeps on happening until the program is into execution and the execution is completed. This process of context switching is costly because 2 MB of data is constantly being loaded and unloaded repeatedly, plus with the size of program goes into execution or application specific data as well. This this also creates one more issue. Creating and destroying operating system threads as and when are costly in itself. So how do we handle that? We handle that through thread pools. In ideal scenario, we want minimum number of threads being created and destroyed. That is why concept of thread pool comes into place. So any application wants a thread, they don't create a thread directly in the operating system. Instead, it talks to thread pool. What thread pool does is, it will check any availability of existing thread. If it doesn't have, it creates a new thread and provides it to the requestee application. Once usage of this new thread is done, your application or requesting application is not supposed to destroy the thread, but instead return it back to the pool, so that it is added to the thread pool of threads and it is not destroyed after the use, so that in future any new application which comes up to request any thread, this can be reused. Also, new creation of threads are minimized, since there are always few extra threads which are there with thread pool. So creation of new threads will get minimized up to a certain point. Let's understand few things about threads again. Threads are costly. Memory required for creation of one thread is 2 MB, almost 2 MB in Linux. Thread context switch is costly. Creating and destroying a thread is also a costly operation. But what happened? We did not have a choice for a lot of time and became a bottleneck for server-based application. Let's suppose there is some application, any simple web application which just simply returns HTML bound with CSS, JS and images. So what happens is, let's suppose there is one client. One client will request is trying to connect to this our web application, creates a request. The request goes to the main thread, and if main thread is executing this, so what it does is, so as soon as the request is received by main thread goes into busy mode and it starts the execution and sends a response to whatever is being requested. But during that time, availability of main thread becomes an issue. So that's That is why if there are two concurrent requests made by two different clients at the same time, either one of the client is not going to get the response here. This is the issue. So how we sort it out? Let's understand this. If main thread is responsible for processing any request through a web application, which in return serves static files such as JS, CSS, then the web server will not be fit for the production, because we are not expecting one request at a time, but we are expecting thousands and millions of requests made simultaneously. In above approach, if multiple requests are received, it will be responded in a sequential manner, and hence it is not optimum for production servers. Hence, it created a lot of issues for developers and for the IT industry as well. So, how does a production server behaves? The main thread will not process the request. Instead, let's understand this. This is a better approach that got implemented. So, main thread is not responsible for executing any request which is being received by your web server. So, what it will do is main thread will spin worker thread, and worker thread will talk to your web server and file system and send response back to the client. Let's say multiple requests come from client 1, client 2 at the same time. Main thread passes whatever the request comes to the worker thread and returns back to the listening mode, so that the new request can be answered and can be passed on to the next worker thread. But let's say if you have two processors, only two threads can be executed at a time. So this means number of requests that can be handled by a web server was being limited by the processor. So thread enables you to process multiple concurrent requests, but not at the same time. Even though you have 500 threads or 500 worker threads, you are still limited by the number of processors. For 500 requests, let's say 2 MB per request. One thread requires per 2 MB, and there are 500 requests which are there. So it will require almost 1 GB of RAM and few MB in RAM for buffer and operational purposes. So how does this problem get solved? In Golang, there is a different solution. The Golang implements an entire different solution to cater all these issues, and hence finally we'll move to understand the Go scheduler in our next video. Thank you for watching.